everyone. Again we are starting a new topic of heat exchangers, and if you can recall that we have started discussing different augmentation techniques, and then we have told that extended surfaces or fins, they are very versatile augmentation technique. They are passive technique, they do not need any auxiliary power, but they can be used in various conditions for various modes of heat transfer on various geometry, and by some innovative design we can have both increase in surface area whenever we are using any kind of extended surface or fin. Primarily we get increase in surface area, but at the same time by our innovative design we can also enhance the heat transfer coefficient, convective heat transfer coefficient. So, there is a double gain in many cases, and we can have a good amount of heat transfer enhancement by providing extended surfaces or fins. And extended surfaces or fins are very extensively used for gas side heat transfer augmentation, though they are used for liquid side heat transfer augmentation or heat transfer augmentation for phase change cases, but mainly they are used for gas side heat transfer augmentation. And what we want to do today, we like to take several examples, because fins or extended surface heat transfer devices are very important. We want to take several examples, particularly numerical example, how the calculation or estimation can be done for extended surface heat transfer. Okay. So, first this is kind of a, it is not truly speaking a heat exchanger problem, but basically a heat transfer problem, but we will have some idea that how fin calculation can be done. Very simple case I have taken. What we have done is like this, that we have taken a fin on a plane surface, and this fin is a very narrow cylinder. This type of fins are called pin fins. So, only one fin is there whose diameter is d and length is L, and all the informations are given here. It is said that an aluminum pin fin of uniform diameter 2 millimeter, length 10 millimeter is attached to a hot surface with a temperature of 200 degrees Celsius. If the fin is cooled by passing air across it at 15 degrees Celsius, resulting in a heat transfer coefficient of 100 watt per meter square Kelvin, calculate the rate of heat transfer from the fin, its effectiveness and efficiency. For doing this, we need the thermal conductivity, and thermal conductivity of aluminum is 250 watt per meter Kelvin. Many of you have done this kind of problems while you have studied heat transfer, but for the benefit of everyone and for the sake of generality, let us have a very simple problem at the beginning. So, data given are this thing, that is diameter of the pin fin is 2 millimeter, length is 10 millimeter. You see, from here you will get some idea, the length is at least 5 times more than the diameter. Then H, heat transfer coefficient, that is also given 100 watt per meter square Kelvin, and thermal conductivity of the fin material, that is 250 watt per meter Kelvin. Fluid temperature T f is 15 degrees Celsius, T b, that is the base temperature of the fin, and that is 200 degrees Celsius. Theta b, we define theta b, that is the temperature difference between the base and the fluid, that is 185 degrees Celsius. Cross sectional area of the fin through which heat transfer takes place, that is pi by 4 d square, and we get this. And then perimeter of the fin, that is a length. So, perimeter of the fin is equal to pi d. So, we have calculated the value. If we go to the next slide now, first we have to calculate the thermogeometric parameter, which is the most important parameter of fin design, that is m. It is under root H p by K A C, where H is the heat transfer coefficient, P is the perimeter of the fin, K is the thermal conductivity and A C is the cross sectional area. Putting all these values, we will get 28.27 per meter, that means meter to the power 1, that is what the unit of m is. So, the unit of m is meter to the power minus 1. For fin having insulated tip, heat transfer is given by the formula given below. See, most of the cases in heat transfer calculation, we are going to assume insulated fin tip. Now, here I like to mention that I have shown the analysis of fin this way only, but there are other ways of analyzing fin. Taking a heat transfer from the fin tip or taking a given temperature at the fin tip or assuming that the fin is infinitely long. So, ultimately it achieves the atmospheric temperature of the surrounding fluid. All these things are there and these are textbook material of heat transfer, any standard heat transfer book. But amongst them, the insulated fin tip is most commonly used. There are many reasons for that. First thing is that in many cases in heat exchanger, we will find that the fin tip is really insulated. That means there is no heat transfer from the fin tip. We do not provide any insulation on there, but the design is such that from the fin tip there is no heat transfer. So, that is one point. Second point, the loss of heat is very small from the fin tip. So, if we assume that the fin tip is not taking part in heat transfer, our estimations are not wrong. Third point is that in many cases what we can do an approximation. We can correct the length of the fin taking into account that there is some amount of heat transfer from the fin tip, and yet we use the formula for fin with insulated tip, because that formula is easier to use compared to using a formula for convective tip loss from the fin. So, that is what we will do in the entire exercise or whatever numerical examples I will present. We will assume the fin tip to be insulated. So, what we have done, we have the fin having insulated tip, the heat transfer is given by Q f fin heat transfer, that is under root H p K A C into theta b into tan hyperbolic m L. M is the thermogeometric parameter which already we have calculated, L is the length of the fin, and theta b also we have calculated in our previous slide, I have shown it. So, putting all these value, we will get K f is equal to 1.1275 watt. So, for a single fin, a pin fin provided over the hot surface, this will be the heat transfer. Now, this point we will come back again in much detail, that on a heat transfer surface rarely we find a single fin. So, there will be number of fins, and in that case we have to calculate what is the heat transfer from all the fins. Not only that, there will be spaces in between fin, we also want to know that what will be the heat transfer from the interfin spaces, then we will be able to find out what is the total heat transfer from the fin surface. Now, for the single fin, the fin effectiveness we can find out what is the heat transfer from the fin and what is the heat transfer without the fin, and fin effectiveness by giving the formula by using the formula which already I have told, and here also I have written. So, it is coming 19.4. So, in simple words, what does it mean? It means that if we do not have a fin and we propose to use a fin. By using a single fin, we can have this much amount of heat transfer enhancement. Okay. Very large amount of heat transfer enhancement we can have. So, this is what is given by this particular calculation. So, this really justifies use of the fin. Then fin efficiency. So, first it justifies the use of the fin, but then let us see how good is the fin we are using. So, there it is fin efficiency, the fin heat transfer and the maximum heat transfer that could be possible by a fin of same geometry, and it is 0.9704. So, it is a very high efficiency. Suppose we decide to use this geometry from some other consideration, then our fin design for this case means the length of the fin, the material of the fin, etc., we have selected in such a way, so that we are getting 97% capability of an ideal fin. So, really one can think of that this design is good. So, time to time we have to calculate the effectiveness and the efficiency of the fin to check whether we have done a good job or not. Let us take another problem. This problem is from the book of Arkesa and Sekulic on heat exchanger. Basically, though it is associated with a heat exchanger, but the problem is one can take is as a simple heat transfer problem, fin problem. Let us read the problem. A plate fin heat exchanger has 24 millimeter high, 0.12 millimeter thick rectangular fins with a fin density of 600 fins per meter. The heat transfer coefficient for airflow over the fins is 170 watt per meter square Kelvin. Determine the fin efficiency if the fins are made from copper with a thermal conductivity of 401 watt per meter Kelvin. If the fin thickness is reduced to 0.06 millimeter, what happens to the fin efficiency and associated heat transfer rate? How would you change the fin density to bring the same level of heat transfer performance with the thinner fins? If you idealize that there is no change in heat transfer coefficient with the change in fin density. Now, change the fin material from copper to aluminum with the thermal conductivity as 237 watt per meter square Kelvin. Discuss the implication of fin efficiency and heat transfer of changing the material from copper to aluminum. The mass densities of these materials are given. For aluminum, obviously it is much lighter, and copper it is having a the density of copper is higher. So, some data are given, heat transfer coefficient data is given, that is 170 watt per meter square Kelvin. Length is given, then copper fins, the thickness is given, then conductivity of the fin Kf that is given, density of fins per meter that is given, and then copper fin we are considering two cases, one is 0.12 millimeter and another is 0.06 millimeter thickness. So, all the data are given. Okay. Now, let us go to the next diagram. So, in the left hand side, how the fins are there in a plate fin heat exchanger, that is shown. So, plate fin heat exchanger, if you notice carefully, this will be explained when we will like to discuss plate fin heat exchanger, but here in connection with fins let us have some idea. So, you see these are two plates, in between there are fins like this. So, you see these are very thin and this one acts as a longitudinal fin. This one acts as a longitudinal fin. And you see, if we assume that both the plates are at same temperature, then one can think of that this is the base of the fin, and here at the mid plane we will have the fin tip at insulated condition. This is very important to appreciate that most of the fins we have seen that it is attached to the base and it goes out of the primary surface and the tip is not connected to any solid surface, but here it is kind of a surface which is connected between other two surfaces which are at 90 degree, okay, which are at 90 degree to the fin. Then there is no free end. So, one can assume as if it is made up of two fins, one fin is attached to the upper plate, another fin is attached to the lower plate. So, this is the base condition of one fin, this is the base condition of other fin, and at the mid plane the fin is insulated, is having insulated tip. Similar thing one can assume. So, if the total length is given B as 2L, then length of the fin will be L only. So, this is what is given in the left hand side diagram, sorry, right hand side diagram. Left hand side diagram, what is there? Left hand side diagram, a very convenient chart is given by which fin efficiency can be estimated without doing an elaborate calculation. So, at the top we have a straight fin whose thickness is delta, length is L, and if the heat transfer coefficient is given and the thermal conductivity is given, then what we can do? We can calculate the this thing ml we can calculate, and as a function of ml we can find out what is the efficiency of the fin for the straight fin. Then below there are number of curves 1, 2, 3, 4, 5 curves are there below the top curve. So, they are for radial fin or annular fin or sometimes they are called circular fins. That means, fin around a circular tube. So, here what we need? We have to calculate m into Re minus Ro. Re and Ro, these two things are given. Okay. So, if the fin geometry is known, Ro should be known, Re should be known, we can calculate this, and m is a thermogeometric parameter. How to calculate m we have discussed, and again we will see how to calculate m. So, if that is known then it depends, fin efficiency of the circular fin depends on me multiplied by Re into Ro and Re by Ro. So, there are these 4 different curves or 5 different curves are for different Re by Ro. Other values, for other values we have to do interpolation. So, with this we can calculate or estimate the efficiency of the circular fin without going into some sort of a tedious calculation which involves Bessel function. So, you know that in the estimation of efficiency for this one straight fin we need to have the hyperbolic trigonometric function, and for the estimation of this circular fin we need to have the Bessel function. Now, if we want to avoid this thing, that can be done for ready calculation, for quick calculation, and then this curve will be very, or this graph will be very useful. So, these are kind of data given for the solution of the problem. So, now let us move to the solution. So, what we have to determine? We have to determine the change in the fin efficiency and heat transfer rate if the copper fin thickness is changed from 0.12 millimeter to 0.06 millimeter. Next thing we have to do, the change in fin density for the same heat transfer when reducing the fin thickness from 0.12 to 0.06 millimeter. And third, how the fin efficiency is changed if the fin material is change from copper to aluminum keeping the same fin geometry, what are the other design implications? What we assume? We assume the heat transfer coefficient does not change if we change the fin density. Heat transfer coefficient, what we are doing? We are changing the fin thickness. Accordingly, sometimes we are changing the fin density, how many fins will be there on a particular length, but our heat transfer coefficient does not change. So, this is one assumption. This assumption is not truly correct, but just to get an idea that what is the effect of fin density, what is the effect of fin material, on this simplified assumption we are working. Okay. So, first let us try to find out the efficiency of the copper fin. We have calculated M, and M you see M how it is calculated giving all the values etcetera. And then what we have done, we have putting all the values, we got 84.057 meter to the power 1, that is your M. So, with M we have got ml, and with this formula we have got the fin efficiency is equal to 0.759. Now, here we are calculating. So, what is the point of having that curve? So, we can go to that curve. I have shown in the previous slide, some previous slide, and let us see, we can I will go back to this curve, and let us see that what we will do from that curve. So, let us say that efficiency for the straight fin we do not want to calculate, we want to get from the curve. So, ml value we have got, and from the ml value we can get directly from the efficiency. That is one way of doing it. I am requesting you to check what by calculation we have got, whether from this curve we are getting the same value or not. Another way that we calculate the hyperbolic trigonometric function tan hyperbolic, and then we calculate the fin efficiency. All right. So, fin efficiency we have calculated, and then if the fin thickness is reduced, obviously our fin efficiency will be lower. In the first case it is 7.759, 75% or 76%. In the second case it is 62%. So, we get an idea that if we reduce the fin thickness, fin efficiency falls. Well, then what we do that there is an 80% reduction. So, what we can do, if we increase the fin density, number of fins per unit length, then we can again recover the same amount of heat transfer. Now, this has been discussed. Now, what we can do, changing the fin material from copper to aluminum, and then all the calculation again one can do, and here the efficiency we are getting 0.659, okay, with our 12 millimeter of, let me see, yes, 12 millimeter of fin thickness, we are getting 0.659 efficiency. So, obviously, from copper, if we switch over to aluminum and keeping everything constant, then there will be a fall in efficiency. Here we got the two efficiencies. We got that there is 18% reduction in heat duty if we move from 12 millimeter, sorry, 0.12 millimeter thickness to 0.06 millimeter thickness, and then we are considering the change of fin material from copper to aluminum. We have kept everything all right, uniform, 0.12 millimeter thickness of the fin, and with that we get an efficiency of 0.659. That means 66% efficiency we are getting, which is less than our efficiency of copper fin, and it is expected. Then what we like to do that we want to make some sort of a comparison. It is like this, that copper is a costly material. Then there were and again it is heavier material. So, there was a tendency, there is a tendency that if we can replace the copper fins by aluminum fins. Now, again there is another comparison can be made between these two material. Copper is having larger strength compared to aluminum. So, the way we can use thin copper fins, we cannot use thin aluminum fins. That means, the minimum thickness of copper which we can use in our fin design, the same minimum thickness we cannot use for aluminum fin design. So, here it is very important, we can see that changing the material from copper to aluminum reduces fin efficiency from 76% to 66%. However, if we compare 0.12 millimeter thick aluminum fin with 0.06 millimeter copper fin, then the efficiency is about the same. That means, let us say we have seen earlier two cases. In one case, we have used 0.06 millimeter thickness of fin, and if we take, that is one design option, and on another side we have got another design option, that is 0.12 millimeter thick aluminum fin, then the efficiencies are comparable. Okay. Now, let us make another kind of a comparison. Now, let us compare the material used for these two fins, that 0.12 millimeter of aluminum fin and 0.06 millimeter of copper fin, and then since the mass densities of aluminum is much lower compared to the mass density of copper, we can make a comparison like this: aluminum fin material, and that is the fin material, this is the density, this is copper fin material, and this is the density. And you see, by comparing them or by taking a ratio, we get 0.6. That means, for same kind of heat transfer, if you use copper, we need to use only 60% aluminum. So, it makes the material use much less, it makes the weight of the equipment much less. That could have some relevance for equipment which are not stationary, which are moving, because the weight, if weight of the moving equipment is larger, then the traction power is more. So, by providing aluminum fin, aluminum parts etc., lighter parts, so what we can do, we can reduce the tractive power without sacrificing the heat transfer. So, this is one point I like you to keep in mind, and with this I like to end today's lecture. Thank you.